Hi there. So I'm Matthew, and today I'm going to be talking about the Jarzynski's equality in a simple steered system. So this presentation is essentially going to go over the following topics. So first, we're going to talk about what exactly is Jarzynski's equality. We're then going to apply that to a simple steered system. So we're going to invent a steered system to apply that to. Next, we're going to show off a little bit of the implementation of that system, and then we'll go into the current results that I have, and then we'll ask, what's next? What can we do for the report next week? So, what is Jarzynski's equality? Essentially, it's a relationship between the work of a non equilibrium process and the change in the equilibrium Helmholtz free energy of a system. And that's a little confusing. So here's a diagram. Say we have a system that's at two times, T initial and T final, right? And you do some work to change from T initial to T final. Well, if you know the beginning Helmholtz free energy, essentially Jarzynski's equality gives you a way to find out the final Helmholtz free energy. It gives you this difference. And we're going to see how that works. So the second law of thermodynamics tells us that this change in free energy is bounded essentially by the mean work of an ensemble of processes. But Jarzynski was really clever, and he found actually like a true equality that involves a thermodynamic quantity here, this exponential, and then adjusting for the temperature. And essentially, what that is that the change in free energy, the Helmholtz free energy, is equal to the exponential of the temperature adjusted change is equal to the mean of the exponential temperature adjusted work, right? So the big takeaway from this is that the change in Helmholtz free energy between states is related to the mean of non-equilibrium work done between states, right? And so there's a couple of caveats with this. One is that the process that we choose has to obey detailed balance. So it's got to be reversible. And we have to start from an equilibrated state. And we also have to uphold the Markov property, right? And that means that the next state of our simulation can only rely on the current state, can't rely on any previous states before that. And so practically, that means that we evaluate Jarzynski's equality or use Jarzynski's equality in the context of the canonical NVT ensemble. And for us, that means we're going to have to use like a Langevin integrator and then also an equilibration period to begin our simulation so that we make sure that we're starting from an equilibrated state. So let's invent a system to apply this to and try it out, right? So this is a really, really simplified version of the literature that I'm doing my term project on. Essentially, it is the minimum viable example, right? And so we're going to imagine a 1D system with two particles, P0 and P1, right? And P0 is going to be located at the origin. And we're going to do everything relative to the origin. And we don't even really have to act like P0 is there. We really just have to consider P1. And P1 is going to be situated at some positive location x with an initial velocity v. The two particles obey a Leonard-Jones potential and force. So we can say that there's a force that's acting on P1 due to P0 simply based on its location x, which will be the distance. And that's because we chose to do things relative to the origin. We'll add another force. Okay, this is going to be our non-equilibrium force that pulls on P1 at some rate, and we'll call that rate V pole. And essentially, the force is going to come from a really stiff spring with spring constant K from some target position lambda to P1. Okay, very, very confusing. But the spring is connected between lambda and P1, right? And we're going to move lambda. And by moving lambda at V pole, we're going to essentially get our spring force. The literature uses psi as a reaction coordinate. It can be really anything that depends on the positions here. Um, because we're doing this minimum viable sort of system, um, psi, the distance between p0 and p1, which is really the only reasonable reaction coordinate here, is equal to x, right? That's equal to the distance between p0 and p1. Right? And really, we're driving psi equals x towards lambda by using this really stiff spring, right? Um, Tracking the mean work that the spring does over many poles using the Jarzynski equality will get us an expression for our Helmholtz free energy in terms of psi, right? And I mean, sort of. Not quite. It's actually a function that's called the potential of mean force, right? It's the potential mean force of psi, and it's analogous to the Helmholtz free energy of the that's related on a position lambda, right? So um, we could say that there is a true function of the Helmholtz free energy of lambda, of positions in space. But the function that we're actually going to be creating is going to be approximate to that because we have this really stiff spring and it's going to follow lambda really closely, but there's a little bit of lag time. So it's not exactly equal. So it's not really the exact Helmholtz free energy. It is approximate, and we're finding this potential mean force, right? And this is just a byproduct of the way that we're estimating this. And that was a lot. So here's a picture. And this picture can sort of help you to understand what we're talking about here, right? So here's our P0, here's our P1. And we give P1 an initial velocity, right? And we set it at a location x, which in our case is equal to psi. And P1 feels a force due to P0, that Leonard-Jones potential force. We're also going to have a point, lambda, that we move at a rate v pole. And essentially what we're going to calculate each time is we're going to pull on our particle, P1, with a spring, with spring constant K, by moving lambda, right? And by doing this, and by tracking the work that is done on P1 by the spring, we're going to get a relationship. We have a relationship between the mean work from a number of trajectories, doing this experiment a number of times, and this potential of mean force function of psi, which is x here, right? And that's analogous to what the actual real Helmholtz free energy is as a function of lambda. And so let's talk about how I implemented this minimum viable example. Important to note is that all of the following code is non-dimensionalized. I've not messed about with units because it was kind of difficult to get this working in the first place. And so let's take a look. So the first part of this is actually coming up with a Langevin integrator, and it's really similar to the velocity Verlet that we did this semester. But we're going to add essentially a random, here I called it a velocity nudge, but it's a random force nudge, right? That is scaled to the temperature of the system and the time step. And that is going to thermally equilibrate our system, right? The Langevin thing is like, it's like putting your system in a heat bath, right? And so it's going to keep our system at the same temperature. We have our system that is thermostated. But otherwise, everything here looks really similar, right? Really familiar. Looks like the velocity Verlet. The only thing is we have another force. We have the spring force. And let's talk about the spring force. So the spring center is our lambda position, right? And we're pulling with a rate of v. And so lambda is changing linearly. So we can calculate lambda at any time, essentially, with this function. And our spring force is essentially going to be Hooke's law applied to the difference between the actual position of the particle x and lambda. And so this is pretty simple. There's nothing crazy going on here, right? We're just pulling on the particle with the spring constant k, and we're pulling based on x minus lambda, that distance that our spring is stretching. If this k is stiff, this should be really small. This should be really close. So how do we actually track the work that's done by our spring? And actually, this is kind of hard. It was very difficult to understand this from the paper. Um, Essentially, what is being done there is like a midpoint approximation due to stepping the simulation. And so we can see here that from time zero to any time t, you're accumulating this partial derivative of lambda with respect to t times the partial derivative of the Hamiltonian with respect to lambda. And the Hamiltonian here is essentially the energy of the spring. This constant part, which comes from the original configuration of the system, is going to drop out in terms of our derivative. And so, really, this Hamiltonian is related to the spring force, and you can come up with this approximation. It's in the paper where you are doing the new lambda minus the old lambda times the mean x minus the mean lambda. So it's like a midpoint discrete integration. And so essentially we're calculating delta w each time and just accumulating that. And we're going to do this for lots of trajectories, and that's going to give us a set of works. And let's actually do that. So let's accumulate trajectories. Here we're putting all the components together, and we're running multiple simulations with an equilibration period to start. We can see this. We set up our particle with a random initial velocity, like we said. We do our Langevin step. So there's a number of equilibration steps that we have. And then after that equilibration period, we pull from our initial lambda to our final lambda, and we're tracking and accumulating the work the whole time, right? And then we essentially have an array of work values, and for each trajectory that we want to collect, we can collect work values. And then we can do statistics on this array, right? We can find the mean work, we can find the standard deviation of the work, we can use Jarzynski's equality to get us to the change in free energy from this initial state to our final state. And here's an example of that, right? Where we have to take the log of the mean of the exponent, where beta is our kbt. Anyway, so if you work backwards, this is essentially the statement that gets you this change in free energy. And we can make a histogram or a plot of the work values that we accumulated from all of our trajectories, and do statistics on that if we would like. But here's an example. And remember, this is all non-dimensionalized, so this number really doesn't mean anything. It's just an example that we have this working. So what's next? Well, I think thing number one is to dimensionalize or use physical quantities. And we could, for example, apply this to argon atoms or carbon atoms or nitrogen atoms or whatever, really. We can do comparison of different pole rates, right? We can look at the change in free energy versus the pole speed and do statistics on a set of different pole speeds, and maybe come up with a relationship between the change in free energy that we observe, right, that delta F value, and our pole speed or our pole rate. If I was feeling really ambitious, and maybe I will get time for this, maybe not, you could try extending this Jarzynski equality or this steered system from two atoms out to a simple 1D polymer chain, with harmonic springs sort of linking each atom, and then at the end you have the same deal where you have this lambda and a really stiff spring pulling on the end, and you're wondering how much work you're doing, right? And then potentially you could do the change in free energy on that whole 1D polymer chain system. And that could be really interesting, but it might take a lot of time, so no promises. But anyway, thanks for listening to this presentation, and I hope that what I was saying was clear. So it's a little difficult for me to even understand, but I hope that it was clear. And welcome any feedback. And yeah, thank you so much. Bye-bye.